Good morning, everyone. Can you hear me? Can you confirm if you see my screen?
Yes, Professor. Good morning.
Good morning.
Hello, can you confirm if you can hear me?
Yes, Professor. We see both the screen and hear your voice. Good morning.
Thank you very much. Thank you. Okay, so we can be ready to start. So you remember what we did yesterday. So I would like to know if you have any questions about what we did yesterday, because today we plan to continue that part. So it would be important to know if something is not clear.
I have a question about the code, if I may ask.
Of course.
I tried to run it, and regarding the fmincon function,
yeah.
when I run it, I got a message like under the function like local minimum found that satisfy the constraints, optimization completed because the objective function is non-decreasing in the feasible direction.
Yeah.
Okay.
Yeah, that's that's not an error.
Okay.
It's just telling you that the computer has been able to find the solution.
Okay.
So it's good that it tells you that.
Perfect. Thank you.
Okay. Anything else? You see, I have the same information on my screen. Okay. All right. Then, if you don't have a further question, I can continue. Can I ask Federico and Felipe to turn the microphone off? You see them here? They have their microphone on. Thank you, Felipe. Also, Federico, please. Okay. No. Felipe, Federico, you should turn your microphone off, not on. Okay. All right. So you remember what was the problem that we sort of addressed yesterday, right? So first, we try numerically to describe all the combination of return and risk, where risk here is measured by standard deviation, that we can obtain, starting from simply for assets, like in our case, the stock of Ford, the stock of Microsoft, the stock of Apple, and the stock of Google. Okay, and this is the universe, in quote, because we only simulated 2,500 portfolios that we can reach. So if you want, this describes available opportunities. Okay. In fact, sometimes in books about portfolios, optimal portfolio, this is called the investment opportunity set. Okay, so basically the opportunities that you have. Okay. Then we said, okay, we need some criteria to choose, the best portfolio, right, for us. And so that's a matter of your taste. Okay, you might be very risk averse, and maybe your criterion is just give me the portfolio with the minimum variance. Maybe instead you want to minimize, to maximize some sort of risk-adjusted return. Maybe you simply want to maximize returns. Okay, so that it's something that the investor will have to choose. Okay, and then we said, okay, we can once we have a criterion, we can sort of like resolve the problem by like what I called yesterday brute force, meaning you know, I have this 2500 or maybe more portfolios that I have simulated, and then I look for the portfolio within this set that satisfy my preference criteria. Okay, so the portfolio among the 2500 which has the lowest variance. Okay, once I have the portfolio, I have the associated weights, and so I have my investment style. Alternatively, we can sort of solve this problem analytically, okay, by basically formally writing an optimization problem, okay. And so if you solve this problem analytically, you don't need all that initial part that I described you, which you sort of simulate, what I call the Monte Carlo, okay. There are two complementary approaches that you can follow. So, and the idea of showing you both is that the first one, I think, is very intuitive, the one with the Monte Carlo, and it's very powerful because it doesn't require basically a lot of, you know, for example, knowledge about optimization. You know, it's simply about simulation. The second is definitely more elegant, but requires a little bit more knowledge of, for example, how to set up an optimization problem. Okay. Second, we looked at the first analytical solution, the one in which we want to maximize the Sharpe ratio. And so you remember, so this is the part that it's in the screen right now. And you remember that I sort of spent some time on two parts. The first part is that this is a constraint minimization problem. So let's try to review together. First of all, why it's a minimization and not a maximization problem? Who wants to help me with this?
Well, we said yesterday that in MATLAB we do not have maximization functions. So to overcome this problem, we just inverse the function and found the mean.
Fantastic. Yeah, that's perfect. Okay, very good. And second, what are the constraints? Do you remember what are the constraints of the problem? Like in simple words.
Like the weight of each stock is bigger than 0 and minor than 1, and the sum is 1.
Perfect. Okay. Yeah, perfect. These are the constraints. Okay, and very good. Who was speaking? So that I remember a little bit of your name.
It's Massimo.
It's Massimo. Well, thank you very much, Massimo. You know, I hope you all remember, like Massimo. So the constraints, so the weights must be basically between 0 and 1. This must sum up to 1, and it's a minimization because of the availability of minimization routines in MATLAB. So basically, we minimize the negative of the Sharpe ratio. So the lines here, 94 to 97, set up the constraints. We discussed them in class yesterday. The line 93 set up or fix the starting point of the optimization, like if you want the initial guess, which I personally set up as the equally weighted portfolio, and then the actual minimization is performed in line 99. Okay, where basically you have this f min con, the minimize constraint routine, that minimize over weights. So weights will be the variable that the minimization will change in order to find the solution. And this min SR, this is the function that MATLAB will try to minimize. now we're gonna open the function. But before we do that, two things. So you see, this is the function, the one that is now highlighted, that takes two inputs, weights, the control variable, and ret, which is the matrix which contains the data, okay? And then this fmin contains some other inputs, the initial guess, x0. Then whenever you see these square brackets, it means that we skip the argument of the function. Then we have all the constraints, and then some options that I told you to leave as in my code in line 98. Okay. You run it, and then the computer very quickly should find what at the beginning your colleague was actually saying, like a local minimum found that satisfies the constraint. Okay, so this is the message you get to confirm that the solution has been found. Okay, and so you see that what is these are the weights associated with the portfolio that minimize the negative Sharpe ratio, that maximize the Sharpe ratio. So basically, you do not invest in the first asset, you do not invest in the second asset, you invest, say, almost 35% of your portfolio in the third asset and 65% in the fourth asset. Okay, so if we go back up in the list of assets, here it is. So you see, you do not invest in the first two, so you do not invest in Facebook, you do not invest in Google. Instead, you do invest in Apple, 35%, and Microsoft, 65%. And by the way, if you look at the plot here, you see that it was sort of expected that you know, if you want to maximize the Sharpe ratio, you do not invest in Ford because it didn't do that well. But you know, it was not obvious that our optimal portfolio would have zero holding of, for example, Google, because Google, you know, it didn't perform as well as say Apple and Microsoft, but didn't do bad either. Okay. All right, so now we are ready to continue. So I see in the chat the comment by Rafael. I don't about importing dates. So this is most likely related to the fact that if you have a Mac, if you have a PC, and you know, you need to go back to the you know, like code that I show you at the very beginning to fix the dates. Okay, so my computer, it works. Okay. Now we can see the, we need to see the second case in which we want to minimize the variance, okay? By the way, so if more than one of you has problem with dates, you know, so that's something you can also like, you know, we can talk over office hour, or you can talk with DTA, okay? Since, you know, it's something mechanical that has to be fixed, okay? So now it would be very similar, okay, minimizing the variance. Similar in the sense that the way we're gonna write the problem will be very similar to how we wrote the problem to minimize the negative Sharpe ratio. So you see, we have again an initial guess, and it's the same as before. So I still use the equally weighted portfolio. I still have exactly the same constraints because the constraints are the same. Non-negative, less than 1, and must sum up to 1. Also, the options, of course, are all the same. Even line 110, which is the key line here, is basically has the same structure as line 99 before. The only thing that changes, of course, is that now there is a new function to minimize, and it's a function that I call here min var. Okay, as before, this function has two inputs. One of the inputs is the control variable, weights, the variable that Matra will try to change in order to solve the problem, and then the other variable is ret, which is the returns. Okay, so let's now open the function that we are trying to minimize, and you'll see that as for the function Sharpe ratio, also min var is a function that is extremely simple, you know, borderline trivial. So you see, The function takes two inputs, weights and ret. It uses these inputs to compute the standard deviation of the portfolio. Okay, how the standard deviation is computed, exactly with the formula we saw yesterday. You see, weights transpose times the variance covariance matrix of return times weights, and I also annualize. So since I'm minimizing the variance, I take this, the power of 2, and so that's the output of the function f. F is the variance of the portfolio. Okay, so it's a basically it's a two-line function. Actually, you know, you can write this in one line, and extremely simple. Okay, and you run it, and again you should find this message, local minimum found that satisfies the constraints. And you see that these are the weights associated with the portfolio that minimize the variance. And you see that differently from the portfolio that minimize the negative Sharpe ratio, now we have a non-negative holding of each of the 4 assets. Okay, so you see we invest almost 24%. Remember, 25 would be the weight associated with the equally weighted portfolio, right? So almost 25% is invested in the Ford stock, 37 in the second, which I think is Google, and then 15 in Microsoft or Apple, and 22 in in the other one. Okay, so you see that interestingly, the fact that we are trying to minimize variance means that we are really trying to exploit the benefit from diversification. And as a result, we are going to use all assets in order to try to reduce as much as possible the variance. We know that graphically, we are basically looking for this portfolio here, okay, more or less, right? This is the portfolio that minimize the volatility, and so also minimize the variance, okay? And we just find out that this portfolio contains a bit of each asset, okay? Is this clear to everyone? Okay. So if I don't hear from you, further question will continue. Now, so the last things we want to do is compute what is called the efficient frontier. So some of you might have, encountered this concept before. So what is the efficient frontier? I wrote here like a, 3-line, 4-line description, okay? So we want to find the portfolios with the minimum volatility for a given target return level. So what does it mean? It means that, I give you many values for returns like 0, 1, 2, 3%. And for each of these values, the efficient frontier will return the portfolio with the minimum volatility. Okay, so basically, given a return, the minimum volatility. Okay, so how do I solve this? Okay, so also this is, if you think about it, is a constraint optimization, because again, I need to minimize the volatility, but I need an additional constraint, and the additional constraint is that the return must be, of the portfolio must be equal to some target value, and it will be an additional constraint to set up in the fmin-conf function. Okay, so before we look at the code, let's look graphically at the problem. Okay, so let me show you. Let me go down a second. So you see the graph here that you see down. Okay, so this is basically, it's going to be the final output of our last basically step. Okay, part of this plot is produced before, because it's what we did yesterday. You remember the dots are those that we produce with the Monte Carlo. Then we have the color that we produce by computing the Sharpe ratio and telling MATLAB to use the Sharpe ratio to identify the different colors. Then you see that you have these two symbols, this pentagon, this star, and this hexagon. This correspond obviously to the star correspond to the minimum variance portfolio that we just found, and this hexagon represent the portfolio with the maximum Sharpe ratio, the one that we found yesterday. And then you see this part here. So these are many axes that I used to plot here. Okay, so this is the efficient frontier, what we want to find out. Okay, why? Because you see that for each values of the returns, you see 0, 2, 0, 21, 0, 22, whatever. Okay, it gives you the portfolio with the minimum volatility. Okay, now something important that I want to couple of things important that I want you to notice. One, in the figure, all the dots that you see are produced by the Monte Carlo, so numerically. Instead, the star, the hexagon, and also this axis here, these symbols are a small axis, okay? So these are produced analytically. And so you see that, you notice that the stuff that we produce analytically, the star, the hexagon, and the axis, they coincide with the portfolios on the Monte Carlo. So this suggests that the Monte Carlo is pretty accurate, okay? Because we could have found this star, okay, also by simply looking at the dots in the Monte Carlo. Similarly, we could have found the hexagon, you see, by looking at our Monte Carlo, and similarly for the axis. So this suggests that the Monte Carlo is pretty accurate, okay? So now we want to learn how to find this axis analytically, okay? You need to just give me like 1 minute because I need to get the charger on my laptop because I realized that I'm running out of battery. Just give me 20 seconds. Okay, so I am attached to the chart. So is it clear the problem that we are trying to solve? Okay, so again, I continue if you don't stop. Right? If you have any questions, anything, feel free to stop. So, as I was telling you before, we want to solve this problem. And so technically, there is basically an additional constraint, okay? Where this additional constraint is this constraint I was mentioning before that says that not only I want to minimize the volatility, given the usual constraint, non-negative weight, weight less than 1, and sum of weights equal to 1. But also, the expected return should be equal to some value. And I want to target value. And I want to repeat this optimization many times, meaning I want to repeat this optimization for each target level of return, okay? So if I go back to the figure here, okay, I'm gonna start with a target value for the return, basically equal to the value corresponding to the minimum variance frontier, portfolio, and then I will go up, okay? For example, from 0 to 0.3, something like that, okay? You'll see in a second. how do we write this second constraint, or this constraint that the portfolio return must be equal to some target value of the return? Well, so in order to do that, you need to understand a little bit the syntax in MATLAB, okay? Because you remember this A, E, Q, and B that we saw also yesterday, okay? If I go back a second here, you see AEQ was a vector of 1, like a row vector of 1, and then in class, you remember I said the constraint is like a vector of 1 that multiplies the weights and must be equal to 1, a scalar, okay, BEQ, okay? So the general syntax in MATLAB is the one that you see here, okay? AEQ times X less or equal than B, okay? So AEQ will be a matrix, X will be our vector of that contains the weights, and B now will have to be a vector because we have two constraints, okay? One entry of the vector, of course, will be 1 because will be related to the fact that the sum of the weights must be equal to 1. The second element of this vector B will contain the target value of the return. You will see better in a second. Okay, so look at this. So line 116, I define a set of target values for the return. So you see I start from 0,2, I stop at 0.28, and I compute 50. So basically I create like 50 equally spaced number in between 0.2 and 0.28. Okay, so that's the range of target return. Okay, you can put less, you can put more, you can put a larger range. That's up to you. Of course, you know, it would be good to have as a maximum for this range the return of the maximum return across the 4 assets. Okay, in fact, maybe I should write this a little better. Okay, and the minimum of this lean space should be the expected the mean return of the minimum variance portfolio. Okay, but more or less, you know, if you look at the pictures, these are the values that you can use. Okay, if you want, you can fix this. Then we need this vector AEQ. Okay, and AEQ. Look at how AEQ is constructed. So it's a matrix that contains. So I know that you are not so familiar with MATLAB yet, okay? So I'm going to tell you what AQ looks like and try to look at the line 118 and try to convince yourself that what I'm telling is correct, okay? So this is what what AQ is. It's a matrix that contains 2 rows and 4 columns, okay? So the first row is just 4 ones, okay? 1, 1, 1, 1. Okay, that would be this part here. You see, ones, 1, and ret. Remember, and ret is the number of assets, so 4. Okay, so this bit that I am highlighting here with my mouse now, so that's the first row of this matrix AQ, and it's 4, 1. The second row, which is these things here, okay, it's also 4 numbers in a row. Okay. And these are the 4 average return on this asset. So the mean return in the first asset, the mean return in the second asset, and so on and so forth. Now, think about, so we don't have now I cannot write on screen, but it's very simple. Think about in your head, you know, try to remember, you know, your knowledge of matrix multiplication. You remember when you do matrix multiplication, you do it's row times column, right? So when you multiply AQ times the vector of weights, okay, so you will do first the row of 1 times W equal 1. That would be the usual constraint. Sum of the weights equal to 1. And then you will multiply the second row, this mean returns, by the weights, so that's the expected return, and must be equal to some target value of return. Okay? Is this clear? So when I do AQ times W equal, B, or BEQ, whatever you want to call it. So the second row is the constraint that the mean portfolio return is equal to some value. Okay? Now, if this is clear to you, look at the loop, which runs from 119 to 128. Okay, so the loop goes for basically 50 times for each value of this target return. Okay, and so look how it works. So for each iteration in the loop, we have to update the vector BEQ, okay, which is part of the constraint, right? The first element of BEQ is always 1, because that's part of the constraint, sum of the weights equal to 1, so that's always 1. The second element, instead, is the target return. And so that must change at every iteration, because it's part of the second constraint, the one that says expected return equal to, say, 0.2, 0.3, 0.4, so we need to update that. Okay, and so that's done in line 120. Okay, and then basically it's about it, because then line 121 is the usual gas, the equally weighted portfolio. Line 122, line 123 is the usual constraint. The lower bound on the weights is 0. The upper bound on the weights is 1. Line 124 is the usual options that you can leave, as it is. And even line 125 is exactly as before. Okay, we have again f min con. We have the same function as before, basically. Well, before was mean var. This is mean standard deviation. It's basically the same. Okay, the only thing is that I don't do the power. You see, that's it. So it's exactly the same as before. That's the nice things. We didn't have to change anything. Okay, even though this part is the same. If you compare line 125 with line say 110, it's basically the same. Okay, it didn't change much. So the only thing literally that we change in this computation of the efficient frontier is the constraint. So that's the only thing you need to learn. Okay, and then so for each iteration we solve the problem, and then I save the weights and the volatility associated to the the minimum volatility associated to each target level of return. Okay, so that then I can construct the efficient frontier. Efficient frontier, remember, is combination of return and associated minimum volatility. So this T-vol will contain the minimum volatilities associated with target rate. Okay, and that's it. So very simple. Now, if the constraint is not clear, I really invite you, then it will, I think if you follow my advice here, it will be very clear. So, follow what I am highlighting here, the dimensions of this AQ, BQ, and weight. And try to write on a piece of paper, like an example, okay, with the matrix 2 times 4 that multiplies the weights equal. Try to do the matrix multiplication. It's trivial. I know you know how to do it very well. And you will see that the way we wrote the problem exactly implies the two constraints that we want to implement. Okay. But I mean, if you are not convinced, you need to do paper and pencil. Okay. It's going to take you 1 minute, 30 seconds, and then you will be convinced. Okay. And that's it. Okay, once you have this T-vol, you can do the plot, which is done here. Don't worry about all the, there is the, some of the things here are like to draw the hexagon, okay, but this is just details, okay, not particularly complicated things, and this is the final result, okay. And so you see that the final result is nice, I think, because it shows you that the Monte Carlo is actually pretty accurate, okay. The analytical solution is very consistent with the Monte Carlo results. We found the optimal portfolio if we decide that we want to go for the minimum variance portfolio. We found the optimal portfolio if we want to go with the maximum Sharpe ratio portfolio, and we found the efficient frontier. Last things I'm going to say before I'm going to ask you if you have any question. So usually the efficient frontier is defined as the part of this overall frontier that starts at the minimum variance. Okay, so you should actually start at the minimum variance and then go up. Okay, so basically this part is also a frontier, but it's not efficient. Why it's not efficient? Because like in the traditional portfolio approach, it would be a portfolio with say lower volatility and same volatility and lower return. Okay, and so that would be the best portfolios to choose, basically. Okay. All right. So now it's good time for you to ask me, any question you might have. Okay. So if you don't have the question,
sorry,
go ahead.
One. So I tried running your code with your data you used, and in line 31 there is it tries to convert the dates with the function of date num, and it already gives me an error. Do you have any idea how that could happen?
So the sound was not great. So you're saying that when you run, you have a problem with the dates? That was your question?
Yes.
Yes. So it's. So do you have a Mac or do you have a?
No, Windows.
Windows. That is strange. I don't know. I mean, maybe you can ask you can write the TA about this. Okay. On my computer it works. Okay. But at the same time, you remember that in one of the first class, we did we spent some time in understanding how to import the data. Okay. So yeah. Here I'm importing the data with the with the read the table. Okay. You can also use XLS read, okay, and maybe with this you should have less problems. I don't know. That's a possibility, okay. But I would have to look, exactly the computer what's going on, okay. So this is my suggestion. Try also to check whether on your Excel file, when you open, the format is exactly this. On my computer, the format is month, day, year, okay. It might be that on your computer it's set up differently, Excel, and when you open Excel it looks differently. So this is it's a bit it depends, say, on your setup. Okay.
Thank you.
But so I'm gonna connect to this question. So for the problem set, basically I'm asking to replicate this. Okay. So try to get the data for like. I think I asked you 5 stocks, okay? Because you remember yesterday I explained that this Yahoo Finance is not working currently. You can even go, but you can still, it doesn't work the automatic download, okay? But you can still go Yahoo Finance and manually download an Excel file with data, okay? So that you can do. You can use Bloomberg if you are on campus. If you go online, there is many sources where you can find, relatively short but free stock data. Google Finance is another one, so any length of sample you like. I mean, it doesn't have to be particularly long, okay? And try to replicate this, okay? I think that in the problem, I also ask you to change it a little bit the constraint. If you are not able to do that part, don't worry, okay? Even if you just replicate exactly what I did, it's fine. But anyway, change the constraint that according to the problem set, it implies basically changing a little bit this lower bound, upper bound. Okay, so it's not complicated at all. But I mean, if you have problems, just replicate what's in this code. But remember, so the way I see it, replicating the code is still useful because it will. I think it will force you to look at these lines and try to make sure that you understand them, which is important. Look, if you are able to, if you understand this, I mean, you've done a lot, okay? So you should be happy with what you've done, okay? Because it means that you know how to solve a lot of portfolio problems now, okay? So that's what I wanted to say. Any questions?
Yes, Professor.
Yeah.
A quick one. So yesterday I was trying to do the problem 1. What I wanted to ask you was all the data that we need in order to solve it is in the 2 Excel files that you gave us.
Yeah.
Right? Okay. Then I must be missing some formula that I'm gonna find because I wasn't quite
If
sure.
you have problems, you write me an email if you still have it.
Thank you.
Okay.
Sorry, Professor.
Yeah.
What is the point from which you told us that the frontier line starts?
The mean return of the minimum variance portfolio. So basically,
Okay.
if you go in this part, right? So you see this in my code is line 113, mu the mean of the variance. So this should be the return from which the in fact, if I want to be more precise, I can replace here. I should put this. Look, I should put this, okay? And so this should be the starting part, okay?
Okay, thanks.
No problem. Any further questions?
Yes, Prof. Excuse me, can you hear me?
Yeah, I can hear you. Yeah, perfectly.
Yeah. Yesterday I'm trying to do it, but I had the problem with the part where we are asking to maximize the Sharpe ratio, because it told me that the starting point of the function is not defined. Otherwise, the minimum variance work properly, and the formulas really the same. So I don't know why MATLAB told
But did you
me
change
this.
my code?
No, it's the exactly one. And we tried with 3 different computers, different data, and always gave us this problem that the starting point of the function is not defined. I don't know why.
That is strange. So that happens when basically you are giving MATLAB a wrong starting value, so that your x0 is a problem. Okay.
Yeah.
But the thing is that
yeah, I know this is strange because with the minimum variance that has exactly the same starting point works. So I don't know precisely why.
So I'm running my computer, my
Yes.
code now. Okay, so this is good. Oh, so I'm having a problem here with because so I was running yesterday on not on my in my office I have not a Mac, and so I was using so I'm having the same problem with dates that some of you are having because of the different computer. So can you tell me what is the line where you have the problem so that I can?
Yes, in the maximize the Sharpe ratio.
Maximize the Sharpe ratio.
Exactly the line 99. He told me that he can't continue to do the fminecon function because the starting point is not defined.
So let's do this. So later today, I will be in my office, so I will run this on the other computer, so I don't have problem with the dates. Okay, and I'll run it and I'll check. In the and maybe if you can write me an email, then I will respond to you. Okay, but in the meantime, try to see what is x0. Okay.
Yeah, X0 is the equally weighted portfolio, and is the same for the minimum variance that works. So,
that's what I would. So basically, my suggestion is that you run the code. When the code stops with mistake, okay, you do this. You copy this. I copy. You go on the command window, and where it's written weights, you write x0, okay, and you do enter, and you see if you get the problem, okay, because that's what the computer is telling you. It's telling you that it cannot do this, okay.
Yeah, exactly.
So try to do this and try to figure out what's the, there must be some small problem here for some reason, and I will also try. I'm gonna be around 11:30. I'll be in my office, and so I can check. Okay.
Okay, perfect. Thank you.
So you will write me an email, because otherwise I cannot respond to you. Okay, so write me an email.
Okay, perfect.
Okay.
Thank you.
All right. So bye-bye, and I'll talk to you very soon. Okay.
We have a lesson today later at 6 o'clock.
Yeah. Yeah.
Okay, see you later. Thank you. Bye-bye.
Bye-bye.